another famous series is the harmonic series, and we also looked at this on the GeoGebra worksheet. If you remember, it looked like it kept going up, but it was sort of slowing down, but it didn't look like yet we could tell if it was going to something or not. And you'll see, actually, it turns out that this diverges. We're going to prove that. But first, let's look at the partial sums just to get some idea, just to compare this with what we did before. So if I have S1, this is 1. S2 is 1 plus 1/2. So that's 3/2. S3, I'm adding up the first 3 terms. Okay, so 3/2 plus 1, I actually did this. It's a pain in the ass. 11/6. So if I look at what's happening here, unlike the previous example where things were actually canceling out and I could see a pattern, in this situation, nothing's really canceling out. And it's hard to think about what the pattern would be. Like, you can see that you got to make a common denominator out of all these things. So you can do the common denominator just by multiplying all those. But what about this top, right? Because each of these has to be missing a number. So it's not like there's an easy way to figure out what this Sn might be in order to try to take the limit for it to go to take the limit to infinity and see if that converges or diverges. So this is where we run into trouble. Even on this very simple example, we can't necessarily reasonably find a form for Sn to take the limit. And that's something that's very, very common. For most series, you actually won't be able to find this Sn. So the geometric series and the telescoping series are special because we can find Sn with just a very little bit of work, but that's very unusual. So what happens here is actually, it's not working very well, right? So somebody whose name I forget, but it's in your book, came up with a little trick here. And this little trick, they weren't really looking just at every single value, but they noticed if I look at the values of Sn, where n is a power of 2. Okay? So I'm going to leave S3 here because I wrote it. I don't really care about it though. I'm just going to ignore it. If I look at this S4, I've got the 1 and then I've got the 1/2. Then I've got this 1/3 and 1/4, right? And what I can notice is that 1/3 is close to 1/4, but it's bigger. So I can do this. Right? And of course, so here are my 3/2. I'm just not going to write this 3/2. I'm just going to call it 1 plus 1/2. So that's my S2. I'm going to ignore S3 for a moment. S4, then it looks like this is 1 plus 1/2 plus 1/2. So this is 1. Okay, I'm really just going to call it 2/2. I know it's 2. But, all right, I'm going to call it that because I want to show you what happens. Because remember, S4 here, we're looking at powers of k, or we're looking at powers of 2. So this is like 2 squared. Okay, so the next power would be S8. So let me write that one down. Okay, and I'm going to do a grouping in the same way. I'm going to group these 2. I'm going to group these 4. So 1/3 is bigger than 1/4, and 1/5, 1/6, and 1/7 are bigger than 1/8. So this whole thing, I do the same thing. I've got 1 plus 1/2 plus, make up this 1/4, And then this other guy, this is a very clever trick. It's not something I will expect you to be able to come up with independently. And it's not something I expect you to really be able to use, but I would like you to follow it so that we can understand how this trick helps us make the claim that this guy actually does diverge. All right? So before you freak out that I'm going to make you do weird stuff like this, I will not. But if you look at what we have here, we have 1 plus 1/2. This one becomes another 1/2. This one becomes another 1/2. So I end up with, for S8, which if we remember is 2 cubed. So this is going to be 1 plus 3/2. And I think if you look in your book, they do one more iteration. They do S16, which would take over my whole board. So I'm not going to do it. But if you look in your book, you will see that S16, which is 2 to the 4th, ends up being 1 plus 4 over 2. So now we can see a pattern not of all the terms, but just of the terms that are 2 to the k. Right? So, and then what we have is that 2 to the k, S of 2 to the k is 1 plus k over 2. Okay? Now, there's a little bit of math here that we've sort of skipped in terms of the fact that we're now going to take the limit of s, it's to be a little s, I don't know why I made my s so big, and take the limit as n goes to infinity, and we're going to show that this, of course, if I take the limit as k goes to infinity, this whole thing goes to infinity, right? So that's basically the thing. It's a little subtle point because we're not doing it for all of the n's. We're only looking at the n's that are powers of 2. But of course, there's an infinite number of powers of 2. So if there are that many numbers in the sequence that are going to infinity, then my sequence has to go to infinity. Okay? So this is a subtle little point which we'll only really see here. So let me just write it. Let me get rid of this and write what I said. So Sn ends up going to infinity, or let me just write it, limit as n goes to infinity, Sn equals infinity, since the limit, okay, this should be greater than, right? Sorry, I lost the greater than in the last part, right? Because we did that weird thing. Since limit as k goes to infinity of your s of 2 to the k is going to be greater than the limit as k goes to infinity of 1 plus k over 2, which is infinite. Okay? So these numbers are bigger than numbers that go off to infinity, so these numbers also have to go off to infinity. And the parent sequence, the Sn, also has to go off to infinity because it contains these numbers that are going to infinity. Fine. All right, so what have we learned by this proof? We have learned that the harmonic series 1 over n diverges to infinity. By the way, it diverges extremely slowly. That's why we couldn't really tell when we looked at the pictures on GeoGebra. It looked like it was going up and it could have been going to something or couldn't have been going to something. Understandable, because this gets bigger very, very, very slowly. But it does eventually get bigger without bound. So that's going to tell us that it diverges. Let's mention the part that I said the wrong word a minute ago because I was thinking about something that I have to say now, right? I said harmonic sequence, okay? So here's a difference between the harmonic series, which as we're adding all these guys up, and just the harmonic sequence. If I just look at the terms individually, right, we know that these terms individually go to 0, okay? But the reason that isn't good enough to tell us that this series does converge to something is because they go to 0, but not quite fast enough to contain the rise in this sum. So it's an interesting case, and it's a case that we'll talk about a lot. It's where the sequence goes to 0, but the series goes to infinity.